Please, all of you, mute yourself. Belum berhenti. Okay, so if you have some mechanism, or if you are already did the part of the kinematics of the mechanisms, then there are two more things that you should do with that mechanism. So first you have to analyze means the dimensions of the mechanisms that will be given to you, and we attempt to determine its motion, how it will move, right? And then the synthesis means the performance requirements of mechanisms are given, and we attempt to determine its dimensions. Okay, so it's like it's kind of an inverse that we are going to do. Okay, so analysis means you know the dimensions of the mechanisms and you attempt to determine its motion. In synthesis, you already know the motions of the mechanisms or what kind of motion you need, and accordingly you will determine what will be the how you will determine the dimensions of it, or you are going to design it, right? So that's kind of analysis and synthesis of the mechanisms that you can do, right? Okay, now analysis part we already did. Now today we will see what is synthesis. Uh, so in type of synthesis, we can see like how you're defining to define kind of mechanisms that is used. It might be kind of like uh, freedom planar motion. Okay, so what kind of mechanisms you can make of it? So you can use 3 RPR, 3 RPR, 3 RRR. So this you can have a PRR here. Okay, so you are seeing all joints are revolute here, 3RR. In here, revolute, prismatic, revolute, revolute, prismatic, revolute, right? So these revolute, prismatic, revolute are 3. Okay. So prismatic is moving the link, means it's increasing that size. It's moving that link forward and backwards like slider you have. And here it is revolute. Similarly here, first prismatic, you're giving the input, and then you have revolute and revolute. Okay. Then prismatic you can have. Okay. Similarly, you can have revolute, and prismatic, and last prismatic, and revolute. Okay. So all of these are giving you 3 degrees of freedom planar motion. Okay. So planar motion means this plate that you're seeing here, the last link which all these links are connecting to, it's actually giving you motion in a plane. Okay. So it's trying to maintain this plate horizontal or vertical in whatever way these three fixed joints are located. Accordingly, you will be able to achieve, right? And the axis of, if you're seeing the revolute, so axis of the motion of those revolute joints will be always be parallel. Then only you will have this in planar motion. Okay. Otherwise, it will be in some other motion plane. Similarly, axis in prismatic and revolute. So axis of the revolute joints will be parallel, while prismatic joints will be totally perpendicular to that parallel. Then only you will get this planar motion. Okay, from these 3 degrees of freedom both. So here's an example. Uh, so this is uh, you can say RRR, and this is 3RR robot. Why 3? So this is revolute, revolute, and revolute, and these links are 3. Okay. So this is a 3 degree of freedom planar motion you are able to achieve. So whatever way you are moving these links, this plate or this field that you have attached with all the 3 links, that will always be in a plane. Even though it can you can move it in some other directions in that plane, but it will be closed workspace and will be in a plane. Okay. So this is one example of type of mechanisms. So for synthesis, so what kind of motion you wanted here? You want the motion to be in a plane, and that motion is controlled by this 3RR mechanisms. Okay. So yeah. Now let's see the dimensional synthesis, how you're determining the dimensions. So to determine dimension of individual link in the mechanisms, what we will do. So here you are seeing an example. So dimension of link 1 and link 2, obviously we want. So what is link 1? So I'm considering where your link 1 is located. Okay. And what is the link 2? So in this case, you will see, actually you have to give the input in one actuator, just at the one revolute joint. Other 2 revolute joints are the consequences of it. You are actually not giving any input over here. Okay. So just where your link 1 is located and how is your dimension of your link 2 will determine what kind of motion you will get it over here. Okay. And the input in terms of the power, or you can say that in terms of motor or whatever you have attached to give as input, that you are giving only at the joint 1, which is just before is in the contact of link 2 and link 1. Okay. So there you are giving the input. So how you will do it? So there are 3 customary tasks of kinematic synthesis that you will do. So first is body guidance, how your body will guide. Function generation. So you have to generate a function so that it will give you the motion of that whatever motion you are trying to achieve. Then path generation. So what path that slider will follow if you are actuating all the 3 joints at the same time with some different angles. Okay. So that 3 functions you have to perform. Okay. So let's see first the body guidance, what body guidance means. So here in body guidance, here we are interested in moving an object from one position to another position. So for example, you can see here, this is A, B, and C. And here with from C, you have attached another hinge uh, to D. And this is B dash and C dash. So if you just move, if you see this B, you can make this arc over here, right? And if you see this DC joint, you can make this arc if you are actuating at A and D. Okay. So here what we are interested in? We are interested in moving the object from one position to another position. And the problem may be called as simple translation or simple combination of translation or rotation. Okay. So if you are moving AB, okay, so it will go till here. And in parallel to that, if you also move this T, what it will do, at this location, it will come up with this part, whatever this part is, that will come over here at this place. So this is B dash and C dash. So so this is for your casting module. Okay, so this example. So here you are seeing, as for casting module, the module will see. Okay, so this is the horizontal position, which is holding the uh, this mold. So it will be like a hinge over here, which is holding this uh, mold plate, which is just compressing this soil over here. And you just have to pull it some way like that. It always come out in horizontal, or you can say, means this plate will always be horizontal. So when it will come out, so when it come out, still some position it will be horizontal, and then obviously you will come out over here, and it becomes horizontal over here. Okay, so we removed the from horizontal position BC, and now we made it to the vertical position V dash. That's what this mechanism is doing. Okay, so the function of now comes the function of function generation. So the task is to make an output member to rotate, oscillate, or reciprocate according to a specified function of time or a function of the input motion. Okay, so here we are seeing this is a kind of 4-wire link which in which you have attached something like with X. So uh, in this example, you can see that we are synthesizing a 4-wire linkage to generate the function y log x. So this y log x function you want to generate. So x is nothing, it's just angle of the input crank. From there you can attain it. And y is the angle of the output crank. So where is your output crank? Output crank is here CD. This is your y. So what input that you are giving is whatever path it is creating, that's you're considering, or input angle that you're considering it as crank, means that's in terms of the angle. And y is what's the output with respect to this x that's coming in terms of the y. So the relation is y log x. So from input link to output link, the relation is this. Okay. So this is the function generation, means if you are giving input to one link, what will be the output in the other link? So that you are generating in terms of the function. Okay. Now, quick return mechanism is a kind of specific function generator. So here you are seeing that mechanism of squaring mechanism. And so what you normally do, let me just show you a video here before going. Yes, my, yeah, here. So I will just show you a video that's for quick return mechanism, and you will get to know how this mechanism is working. So that's on YouTube. Simply you can find it if you want to try it. Okay, let me just share it with you. Okay, so here you can see this is a quick return mechanism example that I will explain to you. So first we will see this small clip, and then we'll go back to our slide, and you will be able to correlate them with very easily. Okay, so here you are seeing that you have this wheel. So in this wheel, you are giving the input. So it's always rotating, either with gears or with belt. With some input motor, you can attach this wheel shaft to rotate. Okay. And when it will rotate, so there is another link. This is a smaller link which will connect with this green small slider over here in this link. So which will slide in this slot. Okay. It's also called it slotted lever. Okay. So in this lever, when your wheel is rotating, because of this slot, this link will act as a rocker. Okay. So it will go till some place and then again it will come back. And because of this rocker mechanisms, this part which is attached with the end of the rocker, this part will move in linear direction. But obviously you have to give some guideways over here, otherwise it can also oscillate. So that you don't want. So just to make that motion, you give the hinge over here to get the motion as a linear, and also some supports or a guideways you can say. Okay. So let's see how it will work. So it's something like this. You're giving the input to the wheel, and because of this slotted slider, it is rocking. So it's kind of a rocker mechanism you are having, and that's why you are having this reciprocating motion over here. Okay, or sliding motion. So this is a quick return mechanism, and it's actually worked on a shaper machine if you have seen it before. So let me just show you a shaper machine. Yeah, this one. So here you can see this is the shaper machine, and let me just go back and go to the mechanism directly. So what this shaper machine does, so you have a work table on which you hold the workpiece, and at the end of this slider which you was moving, so that's called as actually as ram. Okay, and at the end of the ram you attach that tool which always cut in the forward stroke, and in backward stroke it always disengage in cutting. Okay, so just see it more deeply how it is working. So this thing we call it as RAM, and inside the column you have all the mechanism, and this is your work table which is holding the workpiece. Okay, so this is so like this. So I told you that you can give input. So this is your actual crank which is moving, and you can give the input through by any motor or with gears. Okay, so this is the just a pinion which is giving the input over here to rotate this plate, and because of some eccentric distance, it is able to move this link uh, as a crank, or and this link as a rocker. So because of which you are having this motion. Okay, so similar kind of motion you are achieving here. This is a bit of differences over here in the mechanism, but it's a similar kind of motion that you are achieving. So this kind of motion you can get it in shaper machines. Okay. So now let's go back to our slides. Okay. So this is the same thing. It's a quick return mechanism. It's a kind of a specific function that it performs. It's move this slider in the same way. So this is your input crank. Okay, and these 2 points at C1 and C2, you actually change the direction. From C1 to C2, you will not have any, means your stroke will stay at the same place. After C2, it will reverse the direction, until C1, it will go and come back. Okay, so it's like that. So this is like output link moves much faster through the return stroke than it does during the working stroke. So while moving forward, it will be slow, and while return stroke, it will be fast. Okay, so yeah, so there is uh, so this mechanism, I hope you understand how it is working. Now comes the past generation. So the task is that A coupler point is to generate a path having a prescribed shape. Okay, and so this is kind of a mechanism. So here you can see it's uh, hinged at E, B, C, D, A, and these links are also hinged. So what path do you want? So actually the path of point E, this is the point E, is a horizontal straight line that we want. So whenever we are moving this link, it will move in this direction and will bring things like right now it is holding this Q, and when you come from here to here, Q will be here. So but it's always moving in the same distance with respect to this line. Means it's not like it's moving going down. Okay. So the task is that the coupler point means is to generate a path having a prescribed shape. Okay. So this distance E to this block Q, you are always keeping constant. Okay. So it's kind of a crane which is performing this task. And so here you have one link, another link. This is your coupler, you can say, and this is other link. Okay. Extended to the point E, and then you are having the motion which will bring you to here. So this is just 4 link you can see, and this is just the extension of it. Okay, till here. So this will be your E dash, if you can say. Okay. Now, here you have another mechanism, that is blender mechanism. So what you are doing in this blender mechanism, you have this 4-bar linkages. Okay, A, B, C, D. Just this BC linkage you have extended further with some other shape of the link, and that you have connected means when you are having the motion. So because of this point E, it will be moving in this some particular oval shape. And what it is doing is just blending something or mixing something in this bowl, or you can say whatever this block is. So there you are mixing something. So when this link moves, it will always have this kind of motion. Okay, so that's blender mechanism. We can also see it with uh, what you say, one example of this path generation in Mac Analyzer, which I have showed you in first lecture. So that we can go again. Let me just open it. Okay, so it's opening. Till then, we will see other slides. Okay, now in synthesis design methods, in means when you're doing the analytics, you will have high precision from there. So from graphical, you will understand, you can visualize the design. It's like whether it is intuitive, simple, low precision, you're needed from there. And then you will also see environmental perspective of it, like so that's also very low precision you are needed. But in analytics, you will need the high precision while you are doing the designing methods. Okay, so here you are seeing this dimensional synthesis of function generation, and we are talking about the Freudenstein's theorem. So the method is loop closure equation. that you will be following. So this is a 4-bar linkages. So link 1, that's I'm representing with L1. Then similarly link 2, link 3 and link 4. AD is fixed. Okay, link 4 is fixed. The distance between these two A and D points are fixed. And your link is moving like from phi naught, then phi I, similarly delta I, then psi naught, psi I. Okay, so like that your link is moving. So what will be the step 1? So step 1 will be establish the coordinate axis AXY. Okay, so we have created a coordinate axis XY and define the position vector with the vector equation. So first we define the position vector that we already did for the 4-bar mechanism. Here it's again means L1 L plus L2 is equal to L3 plus L4. Okay, the same thing we are defining here again in terms of the project vector, position vector. And then step 3 is project to x and y coordinate axis, and we obtain the two algebraic equation. So this we did before. So is L1 cos phi 1 plus phi naught plus L2 cos delta 1 is equal to L3 cos psi 1 plus psi naught plus L4. Okay, 7 and 7 naught psi naught because we have completed this full motion, that's psi naught plus psi I. Similarly here phi naught plus phi I. Okay, so just based on that you will have this equation of motion. And in y-axis you can write the same thing in like L1 psi 1 plus phi 1 plus phi I plus phi naught plus L2 sine delta I plus L3 sine psi I plus psi naught, right? So from here you can define that L1 by means L1 divided by L1 is obviously will be equal to 1. L2 divided by L1 will be equal to M, that we are defining. And L3 by L1 is equal to N. And L4 by L1 is equal to P. So that when you use this equation, if you are getting these terms, you can just substitute M, N and P instead of these L1, L2 by L1, L3 by L1 and L4 by L1. So like that. Okay. Okay. So what I did, we just take out uh, so what we are doing, we are substituting 3 into 2. So this 3 we are taking just as we have defined and substituting here in equation number 2. And so then we can write the equation again with some manipulation from left to right side, right to left side. So that M cos delta I, because L1 we are just taking it out and putting it, or you can say just dividing it all the equation with L1 and then taking this term over here in negative. Okay, so this will become L2 by 1, which is M. Okay, so M cos delta I is equal to P plus N cos this minus cos this term. Similarly for sine part, okay, so this we have changed. Now what we are going to do, we are going to eliminate delta. Okay, so that delta we will eliminating delta, so we will obtain this part. So cos psi cos phi I plus phi naught is equal to, so this term we are saying is equal to n cos uh, means this term will go on that side, this term will come on this side, simply it's like that. And you will have here n cos this minus n by p cos phi I plus phi naught minus phi I plus uh, phi naught plus n square plus p square plus 1 plus m divided by 2p. Okay, so this you can get. And here we are defining that n is nothing but we are writing it as another constant c naught, n by p as c1, and c2 is nothing but this constant. C2 is another constant which is like this, n2 plus p2 plus 1 minus m square. Okay, so eliminating part, I think you know how what you have to multiply and how you will eliminate it. Okay, So therefore, means this equation, which is over here, we can write it like this, that C naught cos uh, psi I plus I naught minus C1 cos psi I plus psi naught minus phi I plus phi naught plus C2. Okay. So this is how you will get the equation, and you will get the synthesis of function generation. Okay. So yeah, so that's all from the synthesis part. Now I would like to ask Latifa if she also wants to give some input to these slides from her perspective.
All right, thank you.
Yes.
For me, it's enough for the synthesis of mechanisms. Um, Probably on Monday, I can give some examples. But synthesis of mechanisms, what you have delivered, it's enough for me. It's quite clear.
So let me just see if Mechanalyzer is open here. Yes, here. So it's open. Let me just show you it working. Okay. So this is the Mechanalyzer. It's simple 4-bar mechanism that you had, and I have shown you that you can make this thing to make some kind of a curve, or you have seen that example of mixing bowl, right? So L1, L2, L3, L4 is simple, which is making 4-bar linkages. Just L4 means L5 and L6 we have to change. So let's change it a bit. So maybe L6 will change it to, let it be like this. L4 will change it to 0.5. Okay, so after it, but so, is there. Yes. So for example, it is able to be create a path in which it will move. So you can select here whether it could be cyclically, cubic, cosine, take. So these are quite higher order terms, but just for simple explanation, linear, cycloidal, cubic, cosine, or quintic, this is the pattern your path will follow. Means in this equation, so whatever quadratic equation that you will write for your path to follow, that your mechanisms will follow. So if you just do the forward kinematics and see the link, let's say you're going to link 2. So you can define mass and inertia for that link. And similarly for coupler, you can define it and you can see how it is moving. So there is a property of a graph. You can go to coupler and you can see what is the position, how it is moving. So in x direction, you can plot it. Similarly, you can plot it in y direction, how it is moving. So both the positions you can see. Similarly, velocity in x direction and in y direction. Let me remove position. So this is the velocity in x direction. So initially it will be 0, then it will increase and suddenly it will go to positive and then goes to negative, and it will be like this. So that's the curve it will follow. And y direction velocity is like this, some kind of a wave. Similarly, you can check the acceleration, how your acceleration graph is moving. So when you're finding the acceleration for a different mechanisms in 4-bar linkages like this, you can actually check these position, velocity, and acceleration curve in Mach Analyzer, right? So this is for a coupler. Okay, so this is for endpoint on link on the coupler that we are checking how it is moving. Similarly, in Y direction, we can check. Let me just remove other two. So this is the X direction acceleration, and this is the Y direction acceleration. What you have to just do, whatever equation you will find, you just have to replace the time with these points over here, and you will get a similar kind of curve. Okay, so that's one part. Let me just check it. Okay, now let's say if you want to check, okay, how my link 2 is moving, I want to check that. So you're checking endpoint on your link, maybe angular, position, and velocity you want to check. So this is your position, this is your velocity. Okay, so position is going from -100 to +100. It's like cyclical. Then again it will make, if you will change it, it will again make start from here, go back till here, and then so it will make a cycle. Then acceleration is like this. So initially it will be 0, and at the end it is 0. So all these things we check when we are actually planning the path. So path that your mechanism is followed should be smooth. Okay, so you just have to go one more step from here after acceleration, like you also have to check snap and trajectory. So instead of just differentiating it 2 times, you're differentiating 3 or 4 times to check jerk and snap in your mechanism. Okay, similarly for if you want to check linear motion thing in your mechanism, so you can check the position in X and Y direction. Okay, then you can check the velocity. Okay, so that's all. Now let's come back to your mechanism. So what all this I am talking about? So actually when your mechanism is moving, it's making some kind of a curve. Okay, and just by changing this length, you can actually make any profile or curve over here. So that we have seen in your mechanism, in your synthesis part over here. I think not sharing the screen. Yeah. So this example that I have told you, this one. So the same kind of mechanism, this bar has been extended to further. Instead of a straight line, it is some kind of a curve. And because of that, you are getting some oval shape when you are having this 4-bar linkage mechanism moving. Okay, so depending on how you design or how you are making your mechanism, it will depend what kind of path or what kind of motion you will be able to achieve, and from which link you want to take out that motion. Because if you extend this link CD and you want to achieve some kind of motion from there, it will be different from this path, right? Similarly here, if you just extend this AB and attach some point over there, for example, like this, let's say you have just extended it, it's still hinged over there. Because AB is the crank over here, so when it will be rotating, it's actually making full circle. Whether you want that motion or not, it's up to you. So you just have to extend, or from what link actually you want that output, it's up to you. So you can achieve that motion. And that's why I told you that when you go for the design problem, analytics is very high precision. Means all that part you have to do with very precisely graphical. Actually, it gives you the intuition how this link looks. It's very simple to understand, but very low precision. Means in graphical method, you don't have to design it that with very high precision. And experimental is also low precision, because once analytical you did, obviously the experimental part, you will make it precisely whatever you did it, but there you also don't need very high precision over there. Okay, and then comes the synthesis and generation part. So accordingly your mechanisms, how it is made, you can synthesize your mechanism. This is just one example. We have shown it to you here. That's for this Friedrichstein's theorem. and how you can just go about it and make this equation, which will give you the path or synthesis of your function generation, which will give you a path, or you can say the trajectory. So you have to go further for it, means you have to differentiate it for 2 times or 3 times when you will have that motion. First you have to get the equation of motion, then you have to differentiate it, and then it will go further. So it will come in dynamics parts, and Latifa will cover that thing. Okay, so Latifa is there, you are covering this path generation, all those things in dynamics. Okay, so that's all from my side. uh, there are a few more mechanisms. So here is 4-bar Whitworth quick return mechanisms that I would like to show you. Yeah, so this is the one that we were talking about. So it is in a Mech Analyzer. So you can see that how this mechanism is working. The same that we have shown in the slide, it's a similar one. So the slider is moving in this link. Okay. So I will just change the duration, let it move to so that you can see it. Okay, and number of rotation, let's make it 7. So you can see that yeah, here you can see. So you will see that return stroke is so what you will get forward stroke slow, but return stroke is quite uh, slow, right? Let's take another mechanism that is in quick words, that is Ivan linkage. Okay, so it's a similar kind of mechanism, just it's called as Ivan linkage because uh, instead of connecting this link directly over here, you have extended this link over here so that you can have the slider moving. But still here you will have this uh, what is a slider crank mechanism. Okay. So these are all Whitworth quick return mechanism part, and let's see 4-bar quick return mechanism. So it's based on the 4-bar. So what you did here, let me just change. Yeah, so here you have actually a crank, this. So when it is moving, so here you are having 4-bar mechanism, but this link, another link you have attached over here, which is sliding here. Okay, which is giving you the sliding motion just parallel to this bar. So these are different examples of your 4-bar mechanisms and different linkages, and it's up to you what kind of motion you want to achieve from that. So for that you have to just do the analysis. So first you will do the analysis. Okay, if you have particular kind of mechanisms, you can get particular kind of motions from there. But if you want particular kind of motions, for that you have to do the synthesis, means what kind of design or what kind of graphics or what kind of dimensions your link should have, which link you want to extend to get particular kind of motion. Okay, so that's all. And yeah, so for example here that I have shown you, it's the same thing. So you have defined first, okay, I want that kind of motion which can do that. So for that motion, you have to write the equation, and then you can determine this different linkage paths which you can just make your mechanism for. Okay. So yeah, that's all from my side, and thank you all for attending these lectures. And I was quite happy that Latifa invited me for these lectures, and you guys were also quite patient and listening to me and hearing me all these times during the lecture. So I thank you all. Still, if you have any doubt and anything that you want to discuss about what we have covered till now, I welcome you all to have that discussion. Just let me know what you want and if you want to have any question or query that you want to ask. So you can just let me know now. So because this is our last lecture, you can talk about it. So is there anything that you want to talk? Okay. I suggest you to go with the Mac Analyzer software. So it's a very good tool to understand different mechanisms. Actually, you can also do some dynamics part over there, not for all the mechanisms, but for many mechanisms, you can see it. You can plot velocity, position, acceleration curve in linear and angular positions. Uh, means linear velocity, angular velocity. So all those things you can do it there. uh, you can check the path that your mechanisms is following. Mechanisms are already defined over there, but the thing if you're doing the synthesis, that you can apply over there by changing the link lengths. Okay, so that you can check, and you can check whether what kind of motion that you want to achieve, is it able to possible or not. Okay, so that obviously is one possibility is there, but with not all the mechanism it's provided, only with the few mechanism that changes it, that you can do. Okay, so check for it, and yeah, that's all. So yeah, so Latifa, that's all from my side. Do you want to give some input? So, or if any students want to ask some other question or some want to discuss something else related to the topics that we have covered. Okay, so considering you don't want to have any other topic, Latifa, so thank you for inviting me, and I would like to stop it here. I would like to have few comments from your side, and then we can close this lecture.
All right, thank you very much, Deep. Um, so basically, the synthesis of mechanisms is the end of the lecture about kinematics of mechanisms. So all topics have been delivered by Dr. Deep. Now you can see him. Um, well, we have discussed from the beginning about positions, velocities, accelerations, and the last one is about synthesis. Um, and also, this week is the week 12, so we are about a bit late actually. So next week for the students, we'll have a quiz. I will put the quiz on Thursday, because Monday I have another quiz with another class. So I will put the quiz. The third quiz will be on Thursday, and Monday we'll continue with the usual class. We'll continue with the next topic is about dynamics of mechanisms. Please do excuse me. I need to take my chart.
So in dynamics of mechanism, it's just the further you're moving from kinematics part. So in kinematics, you have seen motions. We have seen velocities and acceleration. In dynamics, you will go further with forces and all, right?
Yeah. So that's I will start the dynamics of mechanisms on Monday, and I will give some examples, few examples, how to uh, what happened here? Okay, the dynamics, the examples of synthesis of mechanisms, the topics on how to do it, what kind of theories for synthesis of mechanisms have been given by Dr. Deep, and I will give few examples how to use it for synthesizing mechanisms on Monday. Then I will start teaching about dynamics. So dynamics, the basics of dynamics, you need to know the kinematics. You need to know how to find velocity, accelerations, and after that, you can continue finding the force. Remember, force is mass, the mass times accelerations. So that's why you need to know first how to find the kinematics of mechanisms. That's from my part. And once again, thank you very much for Dr. Deeb. So far, is there any questions from the students?
So Latifa, will you also cover something related to snap and jerk in the dynamics?
I usually just give a general overview. What is jerk? What is snap? And why is it used? But I didn't use it in dynamics so far for dynamics analysis. Even for my research, I just used jerk. Because I didn't really work that much in dynamics. I just started my work in dynamics, and
so you just go to third order differentiation.
Yeah, the third time derivative of positions, and the fourth time derivative of positions are jerk and snap.
Yes. Okay, so thank you everyone, and thank you Latifa for inviting me for this lecture. And yeah,
thank you very much, Tip. Just hold on for 5 seconds. I will need to take photos for all of us. Give your best smile, all of you. Okay, 1, 2. There are 3 groups, so I will take one by one. This is the first one. Okay, let me save it first. Then okay, the next second group is, don't forget to smile. All right, and the last one. Okay, once more, last one.